Compressor wheels, 6-blade splitters, 7-blade splitters, a number of main blades, extended tip, height differences, airflow differences. Today, you're going to learn something. Hey everybody, welcome back. Here's another YouTube video for you. 802 Garage, one of our subscribers, has asked us to do a video on the difference between 6-blade splitters, 7-blade splitters, airflow, etc., etc. I decided to do that for you. I hope you enjoy this video. But here's an intro as to what we're going to be talking about. We're going to talk about the various different blade designs, number of blades, extended tip, root designs, blade area, etc. And just to give you guys a little bit of info, where this information or knowledge comes from is because of the fact that we actually design and manufacture our own compressors in-house, Papa. Now, that little comment is designed or set up specifically for our local market, but be that as it may. So we do design and we do manufacture our own compressors in-house. We do the machining in-house on a 5-axis machine, and we have the ability and equipment to do the testing, from the actual flow calibration to measuring the flow, at the same time being able to plot a compressor map. So let's get into the video. Let me go through the basic features about compressors, which I believe you guys will be able to use at a later stage to look at a compressor in a totally different way next time you see one. All right guys, so what I've got on the table here is a range of different compressors. I've got Borg Warner, I've got Garrett, and I've got our own in-house designed billet compressors on the table, as well as a couple of different materials from cast to billet. And I just want to go over some basic features, the obvious features about these wheels. So some of them you'll notice are 6-blade splitters. Some of them you'll notice are 7-blade splitters. Some of them have got main blades. Some of them are 8 blades. Some of them are 8-blade splitters. Now, I'm going to point out a few things, and I'm going to keep it as layman as possible. Okay, guys, so this is a 8 main blade billet compressor. You'll see that there's no splitter blade. I'm going to show you a splitter blade now, so you guys can become au fait for those that don't know. So this is a 7 main blade with 7 splitter blades separating the main blade area between the two blades. So this is what we term a 7-blade splitter. Here's another 7-blade splitter, 2, 4, 6, 7, and there's obviously 7 splitter blades inside of the main blades. This is a cast wheel. This is obviously a billet machine wheel. Then you have an 11 main blade wheel, a slightly larger 11 main blade wheel, an even larger 10 main blade wheel, quite a small 8 main blade wheel, one of TurboDirect's designed counter rotation 8 main blade wheels, and obviously for those that have never seen one, 2, 4, 6, 8 splitter blades. So this is a splitter blade design, 8 main blades with your 8 splitter blades between. Okay guys, so I've shown you a range of wheels on the table that are different blade configurations, both splitter and main blade, and obviously all of these are different sizes, inducer and exducer, and obviously different horsepower capabilities, different flow rates. For those that don't know, conservatively, for every 10 pounds per minute of airflow that a compressor can generate, that an engine can put to good use, will be able to generate or produce approximately 100 horsepower at the engine, at the crank, not at the wheels. We're talking about the power that the engine can produce. So you'll have pound per minute of airflow differences between the range of wheels on the table here. Now what I want to do is I want to go over a couple of things. I'm not going to go into an explanation as to how the designs and the aerodynamics actually work, but I will go into the obvious features. Okay guys, so what I have here is an original Garrett 60-1 compressor wheel. This is a wheel that is very, very well known for making 550 to approximately 580 horsepower on various engines. It has got a great compressor map. It has got a very, very wide surge to choke limit. It is a very, very good responsive compressor. The blade thickness is really thin. It's a fantastic product. It's proven. We've made upwards of 500 wheel horsepower at approximately 1.4 to 1.6 bar boost on various 2-liter multi-valve engines in our country, in South Africa before. It's proven. Now, what I'm going to do is I'm going to compare this wheel to a GTX 3076 Gen 1. Yes, it's green. Yes, we made it ourselves. Yes, there are differences between the actual blade designs. However, the inducer, exducer, and radius profile on this specific wheel is the same as the GTX 3076 Garrett. There are other differences which will affect the flow rate, but I'm going to talk about this wheel as if it was the genuine Garrett 3076 GTX Gen 1. Now, the 7-blade splitter produces approximately, let's work on a conservative value of 550 horsepower, 55 pounds per minute of airflow. It's actually more, but let's work on that. This specific wheel over here, Gen 1, produces, according to the compressor map, and it actually does do this, 650 capable horsepower. Inducer blades on the 60-1 is 58.5 mils, going on 59. And the GTX 3076 Gen 1 is 58 millimeters. Exducer 76, exducer 76. Extended tip on the GTX Gen 1, no extended tip on the 60-1. What we're looking at here is the tip height of these two blades. Now, what we're referring to is what the vernier, or caliper, as you guys in the States will refer to this as. What we're looking at is the distance that I'm currently measuring on camera right now. Okay, that is what we term the tip height. Right, there's a slight difference in the tip height, approximately a millimeter. Let's talk very briefly about the tip height. It's like comparing blowing through a straw versus a hose pipe. The smaller the tip height, the narrower, the smaller the height, or the smaller the measurement, the higher the P2C ratio. These are the basics. I'm not going to elaborate on that. The higher the tip height, the lower the P2C ratio. Blowing through a hose pipe versus blowing through a straw. Higher volume, lower volume. Higher P2C, lower P2C. Okay, the obvious question is, but hold on a second, this wheel flows more because it can make more horsepower than this. So how is it possible that this wheel will have a smaller tip height and still be able to flow 650 horsepower, and the larger tip height or higher tip height on the 7-blade splitter only flows 55 pounds of air, 550 horsepower? Well, that's one of the things I wanted to point out to you. Next, let's move to the GTX 3582 Gen 1 compressor wheel, which measures 62.5 on the inducer and 82 on the exducer. It also has extended tip. And let's take the latest Garrett G35 1050, which measures 66, 67 on the inducer, and I will need to refresh my memory, 84.5 on the exducer. Let's just verify the inducer here. It's difficult to measure because it's an odd shape. 67, 68 millimeters on the inducer. Now, these two blades obviously have a size difference, but let's have a look at the tip heights. It's a bit difficult because of the extended tip to measure the tip height on the G35. It's approximately 9.3 millimeters versus the GTX Gen 1, which is approximately 7.4. So it's about a 2 millimeter difference. This has got 11 main blades. This has got 2, 4, 6, 8, 9 main blades. Now, if we go back a series to the GTX 3582 Gen 2, that had 10 main blades. So horsepower rating on the Gen 1 GTX, 3582 is 750 horsepower. The missing wheel here, which is the 10 blade GTX 3582 Gen 2, which has got a larger inducer, was 850 horsepower in the volume 7 catalog from Garrett and 900 horsepower in the volume 8 etc. catalogs, obviously the catalogs that come after that. The G35 1050 is rated at 1050 horsepower. What I want to talk about now is route design. I'm going to go to the board and just make a drawing on the board just to depict exactly what I mean by route design. Okay guys, so what I've got on the board here is just a basic drawing of a route design of a compressor wheel. What you're looking at is the piece of material without blades on it. If we had to go and draw blades on this, you would basically have a blade structure that would look like that. And if you had your splitter blades, they would basically sit something similar to that, or they'd actually join up onto the edge over there. So what I want to do is just delete those blades or remove those blades just to get a point across so that I don't confuse you guys and just give you the actual information I want you to know about the route. If I were to take a compressor wheel like this, and yes, this has suffered foreign object damage, but if I remove the blades by grinding them or machining them off without touching the route, you would basically be left with something that looks like what we have on the board. Let's say, for example, we've designed a compressor and we have a route. What part does the route actually play in a compressor wheel? This is the piece or the structure of material that has got the most load exerted on it. So if you do something called a tangential hoop distribution analysis, which is a metallurgical term for analyzing the centrifugal forces exerted on a piece of material, you will find that in this specific area here, you will find the most, actually that specific area there, you will find the most forces exerted on a compressor wheel. And then we go and drill a hole through it, which essentially weakens it even more. So the route design of a compressor is key to the successful or reliable operation of this wheel. Obviously, then you go and attach your blades to it. Okay, so what I want to show you guys now, I've just discussed the route with you and the design of the route. It's critical and key to reliability, etc., etc. I'm going to show you two blades now which share the exact same route dimensions. We make them in-house, Papa. And I want to show you the difference between these two blades. The inducer and exducer of these two blades are different. And obviously the flow rate is different. But I want to go into the next section of this topic, which is blade area. Okay guys, so we've got these two blades in front of you here. This specific blade measures 100 millimeters in inducer diameter and 154 millimeters on the exducer. This blade measures 91 inducer and 149 on the exducer. The total height of these two blades from the back disc to the top of the inducer blade at its widest point is about 2 millimeters. It's 52 millimeters here, and it is 50 millimeters on this blade. So there's only a 2 millimeter difference. What I want to point out to you is blade area. So first of all, I mentioned that these two blades share exactly the same route dimensions. The route dimensions, and I'm only going to take one measurement here, is 34.6, 34.7, round about there at the nose, 35 mils. So they do share exactly the same route. Let's have a look at something really interesting. Now, the flow differences between these are about 25%. Let's have a look at the blade area. That's approximately 32 millimeters from where the blade attaches to the root to the tip of the blade. And from 32 mils, we'll go down to approximately, these are as close as Dammit measurements, they're not exact, 27 mils. So there's quite a big difference in the blade area. Now, obviously, the bigger the blade, the more airflow you're going to find the blade is obviously going to produce. However, you're going to need to make sure that the blade is going to be designed in such a way that it doesn't weaken the blade, or the blade does not get weak or weaker as it extends on the inducer plane. I'm going to leave that there. Right, what I want to do here is just depict something quickly for you guys. We're going to have I'm going to draw two. Just assume that these are identical roots, please. I'm not an artist by any means. So, right, so let's assume that the dimensions of these two roots are exactly the same. I want to show you blade area. Forget about the splitter blades. Now, let's say, for example, we've got these two wheels and we've got a blade area of 32 millimeters from root to tip and 27 millimeters from root to tip. You're obviously going to get more flow from the bigger blade area. So now let's say, for example, we've got a compressor wheel, which in actual fact, this specific 8-blade wheel over here, which was designed for both the KO4 family Borg Warners as an upgrade, as well as the IS38 as an upgrade. We tested two different root designs. So the inducer blades, and I'm going to draw a different picture for you here now. The inducer blades measured, let's say, 45 millimeters. The root design on the one had a dimension of, let's say, 8 millimeters, and the other one had a root dimension of, let's say, 5 millimeters. I'm just using an example here, guys. We've still got the same inducer of 45 millimeters. This specific blade, even though the inducer blade dimension of 45 mils is identical to this one, will flow more. Why? Because the blade area from root to tip is larger than the blade area from root to tip over there. So there's a turbocharger manufacturer in the industry today which has capitalized on this, and I won't mention the turbocharger company's name, but what they've gone and done with their range of turbochargers is they've kept the inducer diameter of 62 millimeters on a specific turbocharger exactly the same, but they've reduced the root dimensions. And that has given them a little bit extra blade area, which has allowed the wheel to outperform its competitor. So that's a little bit about blade area. Next, I want to talk about blade height, and then I'm going to close off. Now, I have a wheel in my hands here, which is the Borg Warner S200 SXE. It's a 650 horsepower capable blade, and it is a 7-blade splitter design. And I'm going to compare that to the Garrett GTX 3076 Gen 1 11 main blade wheel, 7-blade splitter, 11 main blade wheel. Inducer diameter 58, exducer 76. Inducer 57, exducer 76. The main difference between these two blades is obviously the number of blades, but also the total height of these two blades. Let me show you. All right, so here are the two blades. And if you look at them, you'll see that the Borg Warner has a total blade height from the top of the inducer blade to the back disc, which I'll measure for you and show you the dimensions. Try and get away from the radius as it increases over there so that you don't get a false measurement. So we normally just like to do that, turn the vernier at an angle. Looking at about a 31.3 millimeter total height. The Garrett, 26.3. So it's quite a considerable difference in the total height. 640 horsepower, 650 horsepower. Both these blades are tested and got a proven track record, and they produce that horsepower at the engine, at the crank. Now, let's look at the next measurement. I'm just going to ask the questions. I'm not going to give the information. And I hope this generates some brain fluid flowing throughout. 6.6 millimeters tip height on the Borg, and 7 millimeters on the Garrett. There's a 0.4 millimeter difference. Now, here's a question for you. These two blades flow very, very similar amounts of airflow. They're in the same horsepower bracket. This is 11 main blades, this is 7 splitter blades. Could it be that the extra number of blades are doing more work, main blades? Remember, you've got 11 blades with a blade area of approximately 21 millimeters, as opposed to 7 main blades of approximately 20 millimeters doing work. Or is it the difference in tip height of 0.4 millimeters that is responsible for the additional flow? Or could it be the extended tip on this design from Borg-Warner, which is a little bit more aggressive than the extended tip on the Garrett, that is responsible? Or could it be the root design? Now, we've only measured the blade area right at the top. What about the blade area as the root goes down? What about angles of blades? Now I'm talking about the angle of these two blades lying next to each other. I'll turn it so that you guys can get an idea. What about the distance in volume between the two blades, leading and trailing? Okay, so I have another blade design in front of me here, which I just want to show you guys as a matter of interest. It is a 2, 4, 6, 8, 10 main blade design, back to back. This is a single compressor wheel. They're not welded together, there's no trickery here. This specific wheel is designed with a very specific purpose in mind and a very, very clever design compressor housing. So if you look at the blade that I'm showing you to the camera right now, if you look at the orientation of the blades, as opposed to that, one is configured normal rotation, this is the counter rotation, and the other counter. Normal rotation, counter rotation. Obviously, when turning the blade in one direction, which will be in, if you're looking at this blade, an anti-clockwise direction, if I continue turning it in an anti-clockwise direction, the opposite side blades are still turning in the correct orientation related to the blade direction. So this specific blade, 44 millimeter inducer on both sides, has got a compressor map which actually equals approximately a 68 to 70 millimeter inducer on a different design compressor. And the wheel weighs probably a quarter of what the larger counterpart would weigh. Something interesting. Okay guys, so I haven't gone into too much detail on purpose. There's various reasons for that. You know, we have some secrets and we also have information that we want to keep close to our design teams, and our engineers obviously are not going to be very happy if we go and expose all of their hard work, but be that as it may. Compressor design, aerodynamic designs are really, really complex. They're complicated. There's a lot of factors to take into consideration when designing a wheel. It's easy to go and take an OEM compressor that comes out of a BMW and say, well, I want a little bit more horsepower, so make the inducer 10% more and the exducer 10% and leave it apart, and well, let's see what it does, and go to a company in Malaysia to get them manufactured, or in China or in Vietnam or wherever they're made, and get the guys to make you a quantity of 20 or 25 pieces, bring them in and start marketing them locally or whatever the case might be. Many hybrid upgrades are done like that. There's many companies out there that have got 5-axis machining capabilities that will just make a wheel based on, well, a sample you send them with increased designs or increased dimensions on the designs, and then go and market those as hybrid upgrades. Be careful. If a company cannot give you a compressor map that matches a compressor that they've designed or manufactured, question it. I hope you guys have learned something. I hope you guys have enjoyed the limited information that we're prepared to give you on the subject. I think moving forward, if you guys see a compressor, the next time you see a compressor, you'll look at it slightly differently. Hope you guys enjoyed. Like, subscribe. Catch you next time.